Good afternoon, ladies and gentlemen. We would like to start our great debates, and we have quite an interesting topic, so please take your seat, fasten your seatbelt, and be prepared. Just to explain you slightly how we will operate, I will introduce you the panelists, which we are really honored to have here with us. Very knowledgeable people, and then we have a short discussion in the panel about the topic of the debate, and then we will open the floor to the audience. So while the speakers are making their statements, you can prepare your statements as well, or your questions, better your questions. We will after invite people to the microphones. There are 2 microphones in the audience. Please limit your question to 1 minute. So after 1 minute, if you continue talking, we just switch off the microphone. Okay, so now when we are all prepared and all settled and all excited, let me just provide you a little bit of background why we are here and what we wanted to discuss. As you all know, in December 1915, there was the Paris Agreement signed. And that agreement put the goal to limit the climate warming by 2 degrees by the end of the century. And it also speaks about the ambition to limit the warming by 1.5 degrees. Last month, World Meteorological Organization, where I work, released its climate statement. The climate statement reflects the statement of the global climate. And the statement come up with the conclusion that 2017 was the warmest year on record without El Nino, and it has a temperature 1.1 degree above the pre-industrial time, based on the global observations. And we are talking about target of 1.5 degree. The emission gap analysis, which was released by UN Environment last November, demonstrates that even if we implement all the nationally determined contribution, conditional and unconditional ones, they take only 1/3 of the actions which are required to reach the Paris Agreement. In IPCC RCP 2.6 emission scenarios, after year 2050, 2060, 2070, depending which scenario you take, if you look at the emission curve, it's actually below 0. So, the question we have in hand, are we fast enough to achieve our climate targets? Can we reduce emissions fast enough? Are we on track to 2 degrees? And what are the risks if we don't do enough to reach this target? And should we start looking seriously at the artificial manipulation of the climate system? So the topic in hand, which we discuss here, is low-risk geoengineering. Our techniques are available now. And I have the outstanding people at the panel. So on my far right, it's Chris Julin from Uppsala University. I can't turn to you because I need to talk to this guy. Okay. Then in the middle, we have Alan Roach from Rutgers University. And just next to me, we have Frank Schilling from Karlsruhe Institute of Technology. Those are the real experts in the topic. And I just give you the background of all of them, so you understand where they come from, and then they will make their statements. Okay. So we start from Chris. Chris received his bachelor's degree in geology from Brown University and his master's degree in oceanography from University of Washington, and he has a PhD in Geosciences from Uppsala University. He worked for Continental Laboratories as well-site geologist in the Wolston Basin in 1980-1981. During 1986 to 1988, he worked as a geologist for Vattenfall, Sweden. He has held academic position in Curtin University of Technology, at Uppsala University, and he works there until present. And his research interests include crystal geophysics, high-resolution seismic modeling, mining geophysics, geological storage of CO2, and scientific drilling. He's a member of the Royal Swedish Academy of Sciences, adjunct professor of Curtis University, Australia, and guest professor at Julian University, China. Can you wave your hand? Everybody know who is Chris. Okay. Alan, it will take a whole, I don't know, debate to read how excellent you are. So Alan Roach is a distinguished professor of climate sciences in the Department of Environmental Sciences at Rutgers University. He graduated from University of Wisconsin-Madison and metrology, and from Massachusetts Institute of Technology, also in metrology. Before graduate school, he served as a Peace Corps volunteer in the Philippines. I hope it will help us here. He was a professor at the University of Maryland and the State Climatologist of Maryland in 1991-1997, before coming to Rutgers. Professor Roach published 400 articles on his area of research, including more than 240 peer-reviewed papers. His area of expertise include geoengineering, climate effects of nuclear war, effects of volcanic eruptions on climate, and soil moisture. He serves as editor of Reviews of Geophysics. He most highly cited in the Earth Sciences. His honors include being a fellow of American Geophysical Union, the American Meteorological Society, and the American Association for the Advancement of Science. And he is a recipient of AMS July Charney Award. Is it correct? He recently served as a member of the Board of Trustees of University Corporation for Atmospheric Research, which operates the National Center for Atmospheric Research. He was also one of the lead authors of 2013 Working Group 1 Fifth Assessment of IPCC. Alan, can you wave a hand? Thanks. And the panelist who is close to me is Frank Schilling. He graduated in 1989 in mineralogy, and physics, which is maybe not so bad, and received his PhD from University of Tübingen. His habilitation followed in 1998 from Free University Berlin with a Heisenberg Fellowship. He worked at the State Research Center for Geosciences in Potsdam and University of Illinois. 2004, he became a professor for mineral and rock physics at the Free University Berlin and GFZ Potsdam. 2006, he became head of environmental geotechnique and GFZ. And since 2009, he is a chair of petrophysics at Karlsruhe Institute of Technology, where he is the head of the State Research Center for Geothermal Energy, and since 2016, a spokesman of KIT Center for Climate and Environment. Outstanding panel. So, I would like to invite Alan to give us a 5-minute presentation on what is geoengineering and what are the risks. Please remember, we wanted to understand the risk-free technologies. So we speak about the risks. Alan?
Thank you very much. So I just wanted to set the stage for what we're talking about. What is geoengineering? The British Royal Society report 9 years ago now defined geoengineering as deliberate, large-scale manipulation of the planetary environment to counteract anthropogenic climate change. So these words are very carefully chosen. Deliberate means that when last time you drove your car, which caused a little bit of global warming, that was not geoengineering because you weren't trying to warm the planet, you were trying to get somewhere. Large scale means large compared to the planet. So if you paint your roof white or paint your driveway white, that's not geoengineering. 3 years ago, the US National Academy of Sciences released a report on this topic, and it was called Climate Intervention, and they separated it into 2 different books. One of them on the left is carbon dioxide removal and reliable sequestration. And the other one is reflecting sunlight to cool Earth. So the term geoengineering actually applies to 2 quite different techniques. One is to reflect sunlight, the other is to capture the carbon dioxide and put it underground or under the water. And sometimes people are confused because they use that same topic to refer to 2 different things. So it's always important to distinguish between the 2 different types of geoengineering. And they didn't call it geoengineering, they called it climate intervention. The fashion in Europe is to call it climate engineering, which is, of course, more appropriate than geoengineering. But they said they don't even want to use the term engineering, because if you call it engineering, it makes it sound like you know what you're doing. Engineering means, you build a bridge and you make it 3 times stronger than it's supposed to be so it won't fall down. That's engineering. But so they thought we should instead use the term intervention. Intervention is an action intended to improve a situation, but you're not sure what the effects are going to be. So and this picture is true geoengineering, pushing Earth around. So that's also confusing. There are civil engineers who are upset that we've taken their term. So now the fascists call it climate intervention. I work on the atmospheric side, reflecting sunlight to cool Earth, these proposed schemes. And there are 4 that people have studied. One is to put satellites in space to reflect sunlight, and that seems like it's a very expensive and technologically difficult and uncontrollable, and so it really hasn't gotten very much serious consideration. The one that's gotten the most consideration is to emulate a volcanic eruption by putting aerosols in the stratosphere, just like volcanoes do, to reflect sunlight. And we know, based on observations, and our models can simulate that would cool the surface. Volcanic eruptions also serve as an analog for what the risks might be. The other technique which people are looking at is taking low clouds over the ocean and seeding them and making them brighter, and so that would reflect more sunlight over the ocean. And finally, people have even suggested making the surface brighter by putting foam in the ocean or brightening the land. The one technique that's taken most seriously is stratospheric aerosols, and it's not sure that any of these are even possible. No, if you wanted to do it tomorrow, you couldn't. There's no way to create an aerosol in the stratosphere on purpose. We have no techniques to do that. People say it would be easy to design airplanes or other technology to do it, but it hasn't been done yet. And we also don't know how to brighten clouds in a reliable way. So at my first meeting on this topic at NASA Ames, after Paul Crutzen had written his paper that got this research going again, there were really enthusiastic engineers and physicists saying, oh, this is a really cool idea. Oh yeah, we're going to manipulate this. And I started writing down these reasons why it didn't sound like such a good idea to me and might be risky. And I came up with 20 reasons why this might not be such a good idea. And the room at NASA Ames was too hot and nobody could figure out how to cool it down. And it was pretty ironic. We were talking about controlling the temperature of the whole planet. So since then, I've come up with more lists of risks or concerns. And so the last paper I wrote was the 2016 one, and these are all available on my website. And so I have a list of benefits and risks. This is my last slide. And so I think each of these has to be quantified, so if society is tempted to use any of these schemes, they'll be able to make an informed decision. The list on the left is shorter than the list on the right, but benefit number 1 is really important. If you could do it, if you could reduce the planet's temperature, then you could reduce all the negative impacts of global warming. Is it worth accepting all these risks in order to reduce global warming? And that's the decision we have to make based on our research, based on quantifying these. And I've separated the risks into physical and biological systems, human impacts, aesthetics. If you don't have any more blue skies, is that something you want to live with? Unknowns, governance issues, and ethical issues. And so The answer to the question for this session is no. I can't think of any low-risk techniques that we could use right now, but I think we really need to do research to try and understand if it's possible and what the risks are, and are there schemes that actually could be imposed without any risks. And so far I don't know of any, but we're trying to figure that out.
Thank you very much. Now I ask Chris to make his statement.
Yeah, hello, can you hear me? No? Yes, it works. You hear me, all right, okay. So you were looking upwards and I'm going to look downwards and discuss a little bit on how carbon can be stored in the subsurface or in the oceans, but with mainly on focus with carbon capture and storage and the negative technologies associated with that. But there are a number of methods to store carbon in within the earth, and one which I consider to be fairly low risk is afforestation or reforestation, that is planting more forests. Likewise, land management of soils to increase uptake and fix carbon in the soil is also reasonably low risk. The risk that may be associated with these two is that it's not permanently stored. There can be illegal activities like logging and fires which release the carbon again. There's also some ideas on enhanced weathering, spreading out grains of olivine over large areas to uptake carbon directly from the atmosphere. And then there's ocean fertilization. Ideas that have been discussed is putting iron grains into the ocean, which would increase biological activity and uptake the CO2 that way, and the organic matter sink to the bottom of the ocean. And this is maybe more of a high-risk activity if we were to undertake that. Then there's the two negative emission technologies dealing with or having carbon capture and storage associated with them, and that's bioenergy production with carbon capture and storage, or BECCS, where forests or fast-growing bushes are planted. These are then burned to produce electricity. The carbon dioxide is captured and is then stored underground using, if I call it conventional CCS technology, as is being done, for example, at Sleipner today in the North Sea. The other negative emission technology associated with CCS is direct air capture, or DACs, where the CO2 is sucked out of the air using various methods that are being tested or can be tested. And this carbon dioxide would then be transported to a CCS site and also stored underground and removed from the air permanently. So these latter two maybe have a more permanent solution for carbon dioxide storage and negative emission technologies, but they require that we have large-scale CCS, which we don't have yet. And I guess that can be viewed as a risk too, if we are not prepared to build large-scale CCS installations. So that's my view on the situation at the moment.
Thank you very much. Frank, what's your point of view on this question?
I think it's always important to know from which direction a panelist looks on the Earth. So I'm a geoscientist, not from physics, from mineralogy, geology. And So my background is that I had the privilege and to be responsible for the first onshore storage site in Europe for CCS in Kitzin during the permissioning, during drilling, and during the first pumping down of CO2. This took me to the European Commission and Parliament when they discussed the European regulation on CCS. So you probably all know that we have a law in Europe how we have to deal with CCS. But for the project, it was not my main time-consuming part to do science or to ask for permissions. Even at this time, it was not clear if it's possible to get any permission. More than 50% of my time was discussing with the public. You may call it acceptability and acceptance. And if we really want to discuss these issues, I think we should also be very open to hear what other communities think of this issue. So during the discussion with the politicians, it came very clear to me that not all technologies which are technically feasible, which are technically possible, and we just heard about the limitation on size we have at the moment. So how far can we predict? But even if we would be able to do the one or the other thing, we may have severe side effects. At this time, there was a big discussion if we should stop all this pumping down CO2 into the underground and use these aerosol into the atmosphere. So we can pump as much CO2 as we want into the atmosphere, and we simply spray a little bit of particles. You all know that it is much more complex, and there will be side effects, probably for one of the biggest country, the biggest one on earth. They may have drought problems. They may have loss of big harvest areas. And if someone will do that, who will pay for that? This was the question. Who will take the liability for that? Or to take the words Alan just mentioned, is climate engineering really engineering? Do we precisely know the effect, the positive and the negative effect? So if someone is negative affected, that we can pay for them as a global community, and who will be the Lord having all the money to pay for them?
Okay, thank you very much. That's a slightly different perspective. So I will just maybe ask panelists to reflect a little bit on the messages of each other. So we'll start from Chris, and I think in your statement you actually said that there are some geoengineering techniques where the risks are reasonable. So what do you mean with a reasonable? Reasonable for whom?
Well, I think, for example, reforestation or afforestation is pretty low risk, planting trees over. Now, when you start to do it over large areas, you have to take into consideration that land could be used for something else. So there comes a risk in, should that land be used for growing crops instead? But the initial initially planting the trees is low risk. But we have even a bigger problem, and that is we're losing forests rather than gaining forest on the planet. So first of all, we need to reverse that.
Okay. So we should start actually from mitigation rather than going into the technologies.
And I'm sure reforestation would not be sufficient for the challenge we are facing. It's only a small step of the whole challenge.
Okay. Alan, can I ask you the other question? You mentioned in your slides that If we accept the list of the benefits which are potentially coming up with the geoengineering, you have like a different categories of the risks articulated on your slides. How would you actually rank them? Where do you start? Is it like a physical failure or the side effects, or is it more on the ethical, moral side or the political side? What is the most critical one we should look at?
First of all, I just want to say I don't really want to be here because I know what the solution is to global warming. We all understand global warming is real, it's caused by humans, and the solution is to stop using the atmosphere as a sewer for our carbon dioxide and our methane. We all know that, and we know how to do it. We know that we can power the planet with the sun and with wind. So it's really a political problem. There might be a few little issues with a grid and with batteries, but we know, I think we can solve that. But the problem is that that's happening very slowly, as Oksana mentioned. The pledges that the countries have made so far with Paris aren't going to keep us under 2 degrees. So I'd really rather be working on something else, but the question is there a moral hazard? If we figure out a way to do this, are people then going to not worry about mitigation at all? But if we find out that there is no low-risk answer, if we find out that we can't solve the problem with this, that will push even stronger toward mitigation. So I think research is important to try and quantify these risks. So I say to people, they say, what do you do? I say, I work on geoengineering. What's that? Okay, so we're going to fly an airplane over your daughter's school and spray sulfuric acid in the air, and that's going to stop global warming. Really? You're thinking about something that crazy? Well, maybe global warming is really a problem I should really consider more seriously. So maybe there's a negative moral hazard. So to answer your question, I wrote a paper several years ago. There was a meeting in University of Montana. They said, will geoengineering ever be used? Will solar radiation management ever be used? And I think the most insoluble problem is how do we set the global thermostat? For young people, this is how we used to set a thermostat. What if some northern countries, Canada, Russia, want it to look a few degrees warmer, and islands in the tropical Pacific that are drowning want it even colder than it is now? How do we agree on what the planetary temperature should be? And even if we figure out a way to cool it a little bit, but there are mostly winners, but a few losers, as Frank said, how do we compensate the losers? There's a very bad record of compensating people when we do urban renewal or when we build a dam and people are moved out. And it's a long time scale thing too. It's not just immediately, it's decades, and who's going to be responsible? So I think the governance issues are really important, and also the unknowns. If anybody was in a car recently, did you wear your seatbelt? Okay, so if so, you understand the principle that anything built by humans or operated by humans can fail. Would you trust the only planet we know to have intelligent life on one technical solution, very complicated one? So I think the unknowns and the governance issues are really much harder to figure out than can we design a pattern of where to put the aerosols to keep the polar equator temperature gradients from changing.
Thank you. Frank, can you please elaborate a little bit on the acceptance and acceptability? Why you spend 50% of time persuading people? They don't see this carbon. You just dump it in there. It does not impact any way their style of living, or they even don't know. It doesn't stink, or what's the issue?
You know that. They have to know that. So I think a lot of the knowledge which is here collected in the room, if we would have all this in all people's mind, we would have already the solution. So maybe it would be sufficient that some politicians would have this in their mind and not step out of Paris Agreement and say, yes, we want to make America great again, and not only US. So if we would fix the problem, as Alan just mentioned, from south of South America to Mexico to Alaska, and think of the whole global system, then you would have the whole length. So I think it's big issue for us to explain the people in a way what we want to do, what we already know, and also what we don't know. As Alan just mentioned, the unknown unknowns. As scientists, we don't like to say, sorry, I cannot answer this question properly. We have unknown unknowns, and we have to deal with unknown unknowns. And what we do at the moment is very simple, and that's you can explain to the public. We know that at least the colleagues from physics told me that Arrhenius was right, there will be global warming. His only question was how quick, and you are, I guess, much better now on answering Arrhenius' PhD thesis. So, to explain, yes, we run into a problem. Then you have people who say, if we have 2 degrees of global warming, all life on Earth will be extinct. So we all know that's not the truth. There will be winners, there will be losers. And the problem we are facing, we have more than 7 billion people to feed, and most of them live south of the Alps. Why do I mention the Alps? There are some ideas that the population living north of the Alps will have positive benefits, and people living south of the Alps will have negative benefits. Now, Russia, Germany, we are fine, Austria as well. Italy, Spain, Morocco, Mexico, South America, Africa. And then there are 2 countries which may be not as big as Russia or US, but they have more than 1 billion people living there, China, India. So this is what we know. This is not an unknown unknown. But the technologies we discuss here, they have a sort of known issues. But do you really want to extrapolate your knowledge you have gained in a centimeter scale or 1,000-ton scale or 100,000-ton scale more than 10 times per step? So my view on scientific history is whenever you have the chance to get a 10 times higher resolution or to be able to look in a 10-fold dimension, you gain new insights, Hubble telescope or electron microscope. And the same happened if you go step by step in such a technology. You need to go step by step. You cannot start with 100,000 tons and then say, I can handle 1 billion tons. We need the steps in between. And to discuss risks, it means we can discuss the risk for a 10 times bigger storage site. But most of us won't be able to discuss in a serious manner 100 times bigger storage site, 1,000 times bigger storage sites. And that's the dimension we have to deal with, where we have to tackle other challenges than we have in standard gas storage, what we also do with natural gas and things like that.
Okay, thank you. And I think now you got really good understanding what we are talking about. So I would invite the colleagues to come to the microphone and ask the question to the panelists. So there's one microphone up front and one on the back. Please go ahead. Just introduce yourself briefly and use 1 minute for the question.
Yes, I'm Eric Gilliardi from IPSL in Paris. I have a question related to the timescales, because we know basically we have another 1,000 billion tons to emit of CO2 before to stay below 2 degrees. At the rate we're emitting, that's 25 years. So some of these, even the CCS techniques or other techniques may help us at the end of the century, but not in the next decade. So this time scale is not usually, well, maybe you can give us some insight on those 2 time scales, the next couple of decades where we need to act boldly and the end of the century. So.
Well, thanks, Eric. The solar radiation management techniques basically would act instantly. If you can put a cloud up in the stratosphere, volcanic eruptions do it, within a year the planet cools. So that's a technique that could be used quickly. Of course, the aerosols fall out. They have an e-folding lifetime of about a year, so you have to continuously replenish them basically forever. So that's one of the problems. Carbon capture, as you said, would take much longer. It's not the rate of emission, it's the concentration of CO2 that matters. And so once you start taking it out, even if you could stop putting it in and you started taking it out, it would come back out of the ocean because the ocean wouldn't be in equilibrium, so you had to take it out of the atmosphere and the upper ocean eventually, and so that would take a long time. So the only rational idea I know of how to actually use stratospheric aerosols is to do it for a restricted period of time while we figure out how to do mitigation and carbon capture. Not forever, but to shave off the worst impacts of global warming, maybe keep the global warming at 2 degrees rather than 3 or 4 degrees, and while we work on these other techniques.
Okay, we take 2 more questions and then you can elaborate, okay?
I can just add a point on carbon capture and storage. To get it up to the scale that we need, we're looking at least 20 to 30 years from now, and this should have been done a long time ago to get started.
We lost 10 years. Yeah.
Okay, let's not lose time. Please introduce yourself.
So I'm Mike Burton from the University of Manchester in the UK. So I've got a hypothetical question. I'd understand if the panel has trouble addressing this, but we often see, and you've alluded to very clearly, that between politics and science, there's often a different language and definitely a different mentality. One of the risks that we face is there's uncertainty looking forward and forecasting the climate. But in a scenario in the future in which the climate change had a real impact on a major economy, and so you're looking at a real GDP loss, depending on the dynamics of that and the speed of that, but in a scenario if that happened quickly enough, there would be an immense political will to do something, to have an intervention. And my question is twofold, really. One is, what do you think people would jump to first in that kind of scenario? And secondly, what's the moral implications for scientists who are asked to participate in such a project?
We take the next question and we address both of them. Please go ahead.
Oh, that's a big question. Why don't we answer that first?
Can you please? Yeah, go ahead.
Hi, I'm Michael Diamond from the University of Washington, Seattle. I wish my question was a little bit more tied to that, but maybe the panelists will find a way to tie it in. This is mainly for Alan, but I think everyone will have a really interesting response. So the concerns we have listed on the screen right now are for stratospheric geoengineering in particular, especially those governance concerns. I'm wondering if you think those same governance concerns apply to carbon storage as well as solar radiation management, or if you think those are very specific to SRM.
Thank you very much. Okay, I let the panel to answer those 2 questions.
So first of all, I think we lost 10 years in development. So the major problem is that we have different time constant. I liked your introduction, Alan, about engineering. Engineering is knowing what we are doing and knowing the boundary condition and where we end, as long as we are honest to ourselves, knowing that we do not know everything. It's always clear. But to make a proper path, we have to continue step by step to be able to tell in 10 years it's possible with this and that risk. At the moment we can tell it's an option, but we are far away to have all the data available. If now the first bigger economies will have a loss in their GDP, for some state it may be 80% decline, some people say. So I'm not from economy, but this is rather immense. Then they want to have quick answers, and this makes the thing much more risky than making a slow path. So we can conclude in 2 ways, and I understand the people sitting here in a way. We know that this is a challenge. But if we as geoscience community would argue all in one direction, we need to test the different paths, the different options we have globally. It's not a local issue, it's a global issue. Then we may fit to the timescale of policymaker decisions. Their problem often is if they hear 2 or 3 voices, they hear 3 different opinions. And so maybe it's not a real debate, because I guess we agree on many issues. For example, we need more renewables faster, more storage options faster. But none of us, I believe, is able to really know all the risks involved. And therefore, we need to align to this issue and not talk in different manners. We need to be one community, like the physics community. They built CERN, which cost more than $1 billion. No problem for them. They built Hubble. So we have Hubble telescope, we have CERN, but we have not a 10 million ton storage site, which would cost maybe the same. But it would help us to judge if we can go further or not. So if we want to solve the problem like nuclear waste, like these issues come from a scientific sound and engineering sound perspective, which needs also some time.
So there's a lot of questions. Let me just say, we had a Gordon Research Conference in the United States last year, and the program manager for the National Science Foundation for Engineering was there. And at the end of the week, I said, "What did you think?" He said, "Well, this was a conference on geoengineering, but there wasn't much engineering here. It was all about science." And so most of us do indoor research. We sit in front of a computer and we run climate models, we study volcanic eruptions, but there's not a lot of outdoor research. In fact, I don't know of any outdoor research as far as geoengineering. David Keith has proposed a balloon that may be launched next year to do something very tiny, but can you fly an airplane up into the stratosphere, spray out sulfur or something else and create a cloud? How hard is that? I learned at this conference in Berlin in October that existing airplanes cannot be retrofitted with bigger wings or bigger engines. You have to design a whole new class of airplanes, and that seems like the technology that would be the easiest to create this cloud. Can you spray salt into clouds over the ocean and make them brighter without dissipating the clouds nearby and having the net effect that you want? And what would be the regional impact of that? So I think we need a much bigger research program, which is really cheap by any sort of standards, on the order of millions of dollars or euros, not billions, to find out if these things are possible and how hard they would be. And if we find out that they're really hard or that the impacts, the side effects would be really bad, then we can sort of cross this off and forget about it and work even harder on mitigation. But as long as people think that this is an option and we're still sort of slowly trying to figure it out over the next couple of decades, that's not going to serve anybody very well. So I think we really need, it's very self-serving to say we need more money for research. Everybody in this room would agree, I'm sure, but... Well, technology development is still research, I guess.
So the question was like, do we need to wait until we have 80% loss in GDP to do something?
Well, if there was a catastrophic climate catastrophe, say all of a sudden there were many, many more hurricanes starting and people blamed it on global warming, although the talks I heard yesterday said that that wasn't going to happen. But what if there was something like that, or there were major droughts and they could attribute it to global warming? Then there would be a demand, I guess, for immediate action, and carbon capture wouldn't do it because it would be too slow. So what could you do? And let's build a fleet of airplanes or pipes or something, or balloons to block out the sun as quickly as we can. And then somebody else says, well, my country was fine until you did that, but now I'm having terrible floods. You better stop, you damn geoengineers, and if you don't, I'm going to shoot your planes down. So it could get quite complicated quite quickly. Again, the solution might be riskier than not doing anything.
Chris, can you answer on this legislation between the solar and the carbon storage? Or Frank, do you want to answer that question?
I didn't want to answer the question, but Alan said we need people doing real experiments. Can everybody stand up who has been involved directly in such a storage experiment? So. It's very simple, it's not enough. So that's the expertise we have here in this great room with great experts on many issues. We need to get things done, and this means education. So this was an educational part. I'm teacher, sorry. And therefore we need a lot of more expertise to deal with the risks. We talk about risks, but not all the people want to deal with these risks, and they say, I prefer to stay to make full form inversion. That's more safe. Sorry.
I can just add a comment here concerning CCS. And when we say CCS, we often think of burning fossil fuels to generate electricity, but there's a lot of CO2 coming from the industries that are needed to make the change to renewables. We have the steel and cement industries that emit a lot of CO2, and these need to be kept going for a long time to come, and that CO2 needs to be taken care of somehow. So I think a future without CCS is a future with more than 2-degree increase in the temperature.
Okay, so we take a couple more questions from the audience. Please go ahead.
I'm Claudia Wieners from Utrecht University, and I have 3 short questions. So first, what is actually the concern of the public against carbon capture and storage? Why are they so much against it? Is there any real danger involved with that? And second, is there a limitation to the capacity of carbon capture and storage underground? And third, how about these measures about afforestation and so on? Is there a limit on the capacity of these ones?
Do you want to fast run for these questions because there are 3? 3 in 1.
So it's how you do it. It can be high risk or low risk. So if you look at the air buckle field, for example, where you push down a lot of fluids from shale gas production, so the water, the wastewater, you have seen this increasing earthquakes. So you have to deal with these issues if you go big scale. So there are issues, but I'm pretty sure that, and that is what the legislation is all about. So read the legislation 2009 CCS directive that's written how to deal with most of these issues. It's, for example, you need multi-barrier systems in Europe. It's not allowed to have only one barrier because we said it's important to have a second one which acts a little bit different. So if one fails, you have a second one in operation. It should be deep enough, so to have long enough time scale. So there are some issues you have to handle with, you'd have to take care of, and then security also always comes with money. So it may cost a little bit more. And the good storage sites, I can tell you exact numbers for Germany, for example. We will have enough space for 1 generation of coal-fired power plants for the electricity. So the answer is, we have a limited space. So if we continue blowing CO2 from all processes where we don't need CO2 into the atmosphere, like coal-fired power plants, we will have not enough storage space if we simply make a business as usual scenario for the next 50 years. We will not have enough storage capacity which is safe enough.
I can continue on the forestation question that you had. There are estimates on all these technologies on how much CO2 you can remove from the atmosphere, and how realistic these estimates are. I don't know, but some estimates for reforestation and afforestation, they're up to the equivalent of 10 gigatons of CO2 per year, which sounds extremely high, but these are some of the estimates that are being thrown around. So it can have a significant impact on CO2 removal. Then the question is, what are the risks with planting so much forest?
But afforestation, so once you grow the trees, what do you do with them? I mean, that's only a one-time shot, isn't it?
Yes, this is something that would be valid over a certain period, and then you need to leave them there.
Or you make floors and doors out of them, or bury them or something, and grow more.
Houses built of wood instead of concrete. Yeah. This would make a difference. It's not ridiculous, because
my house is wood.
You also have. You are an American, but you live with renewable energies.
Yeah, I have solar panels on my roof. I don't.
Yes, so.
Okay, let's take another question, please.
Martin Bohle, International Association for Promoting Geoethics. Isn't it that there is the risk number 28 is missing? Sound science, sound technology, sound governance. When I draw on the discussions here, I would advocate to bring the term engineering back, because engineering means you know what you are doing, you put safety margins in, you have publicly regulated, and on top you are commercially and privately liable. So for me, geoengineering is, or engineering gives the right message when we take really the sense of the world.
Thank you.
Yes.
Alan, you don't like engineering?
Oh, no. If it were engineering, that would be great. But what we're talking about isn't engineering. It's yeah.
Okay. More questions?
Hi, I'm Sathe from Rostock, University of Rostock, Germany. So I had one question with regard to the deep storage of carbon. Like, let's say in Germany, Professor Frank, you said, in Germany you have this much storage that's possible. So hypothetically, if all of the storage was completely full, what would be how likely do you think it is that it would be suddenly released, causing more harm than good through earthquake or some other way?
Big CO2 explosion.
Well, if one were to proceed logically with this, one would fill up the storage sites closest to the sources to begin with. But Frank is talking about Germany with the limitations within Germany. There's our cousin Norway, who has a large amount of storage capacity, probably the largest in Europe. And they could handle the CO2 requirements for a considerably longer period of time, taking into account Germany's needs also.
So the
sudden release,
yes.
like.
Well, okay.
So it's a design question.
Engineering.
So we are back to engineering. So if we know enough about the system, we can engineer it to a certain level. And if I understand the climate research is correct, it should be less than 1% in 100 years of the release. And so you have different trapping mechanisms. So to answer this question for any location is not possible. But if you look how much of the natural gas from volume can you get out of the pore space or oil, it's only a fraction because you have surface tension. So this is a physical trapping which will help at least 30 to 40% inside the storage site, but it will strongly depend on the site where you look at. Then if you solve a portion of the CO2 into water, the density will go down. And one of the few things I really believe in is that gravity works. So this means that this higher dense material has the tendency to go down, not upwards. Then you have the caprock, and it's at the beginning, it's a lot about the quality of the caprock. But we have a lot of experience with gas storage sites for methane, where we have not all this mechanism to hold it back as we have for CO2. And if you have a second barrier, if you go into a region with a very high seismic risk, let's say you build the storage site directly above San Andreas Fault, maybe it's not the best thing to do. So if you would go, as Chris just mentioned, for example, beneath the sea level, if you are beneath 3,000 meters, there is no tendency for the CO2 to migrate upward because the density will be higher than the density of seawater. And if you have sediments, and if you can go beneath the sediments, you will form, if your cap rock is not tight enough, by the migration you will form gas hydrates, which are stable under these conditions. So it will strongly depend where, what you do, how you do it, and how you operate, and how you surveillance the whole stuff. That's all about engineering. So you have boundary conditions, and if you come too close to critical point, you can get real problems, and therefore it's a task which needs good engineering.
I think I will ask the dessert question to the panel, and then they can make their final statement. We're discussing here very fine and very nice technologies, and theoretically that can work, and some can be low risk. There are about 200 countries in this world, and we are discussing the stuff which is happening only in two, Germany and Norway. What about the rest of the world? So that is a question to the panel, because the issue is global. So what is about the rest of the world? We have G20, but the emissions are rising in Africa. What do they do there? There are large emissions related to oil and gas in Nigeria. So what do we do in those countries? Who will help? Or do we leave them alone? And then when you answer it, you can make the concluding statement as well.
So the solution to all this is a political one. It's a gradually increasing carbon tax. I mean, we don't pay, you pay to have the trash taken away from your house, but nobody pays to a fee for putting carbon dioxide in the atmosphere. Other pollutants are regulated, but CO2 is not. It's invisible, and so politicians are not very happy when they advocate for taxes. They don't get reelected, so we sort of have a problem. We need really, but if the world can agree that gradually there'd be an increasing price on carbon, that would be a huge incentive to produce the technology for developing countries, for the world to produce energy without dumping CO2 in. And if you can have a fee that's returned to people so the governments don't take it, but that everybody gets the same amount back, then people that use less than the average would make money on the deal. And so you really need a visionary leader to actually solve this problem and lead people in that direction. I think the Paris Agreement was a really good step in that direction, and I think that in 2020 there's going to be another conference to revisit that and see if countries will make larger pledges. Each country on its own has to decide how to satisfy these pledges, but if there was a way to make money on it because there was a tax on it, then a fee, then people could really, that would solve the problem. But here we are without it.
I also think if you look globally, there's an obligation for the richer countries to transfer technology to the less well-off countries, so that when they build up their economies, that they do it as intelligently as possible concerning their CO2 emissions.
So I was asked before about the release of CO2. It doesn't mean that there are not other obstacles with the technology. It was only the answer for your direct question. When we were 10 years ago in South Africa, one of the emerging countries which release a lot of CO2 into the atmosphere, they are privileged with the great nature, with the great geology. So they have some options. We told them 10 years ago, why not pumping the CO2 in a deep laying aquifer in 2-3 kilometer depth close to their capital? Because this aquifer is a sweet water aquifer. And at another place in South Africa, they have the problem not to have the water table anymore, which is Kapstadt. It's directly linked. So I bring this example, not that this is a solution. I don't say it's possible, but you could think of things like that, and it may show you the dimension of the challenge. We are talking about billions of cubic meter, and we need a system which can withstand them, and we should always look if we can have also positive side effects. So you will need a solution for different places, for different sources, and geology is not the same everywhere. I don't need to tell it to this audience, but then sometimes people think you can do it everywhere. And I think a second big issue in this respect is that we rather often discuss to people we don't know enough of our underground because we want money for research. But if we would be honest, we know a lot about our underground. If you want to drill down here 3 or 4 kilometers, I'm pretty sure that we would know precisely, precise means here maybe 20 meters wrong, where which formation will appear. We know a lot. We do not know enough, but we know enough to make first steps.
Okay, so if the panel wanted to answer in one sentence, low-risk geoengineering, are techniques available now? Yes.
I would not talk about risks, I would talk about resilience.
Okay.
And our system needs to be resilient, which means we have to deal with the risks of the different technology and how they evolve. And only if we have really all the technologies in place and develop them simultaneously, we really gain a higher resilience.
Okay.
Well, the short answer is no, but what we're doing now with emitting CO2 is risky too. So we're going to have to make a risk-risk decision at some point whether ever to implement these, and we need to know more in order to make that decision.
Chris, can you give simple answer? Yes, no.
Life is risky. But I think we need to start implementing some of these technologies and testing them on a larger scale than what we've been doing.
Okay, so let's take a vote. Can those who believe that there are low-risk geoengineering techniques raise your hand?
For how much capacity?
It's a general question. Good. Excellent. So we need to test those. With that, I would like to thank the panelists. If you still have some questions which you did not dare to ask in the room or which you think as an afterthought, they will be here in the Congress Center. So if you catch them, you know their faces, you can ask them the question. And thank you very much for attendance. Thank you. I should have asked that question.
I told you, if we are prepared, it won't appear.
Oh, yeah, that's wonderful.